Slack channel for this talk. And also just a reminder, yeah, so the Zoom questions take a while just because of the back and forth and the connection's a little bit slow. So unless it's really burning, please leave it to the end. And if you're asking a Zoom question, you may be nodding behind the screen, but we can't see that. So, just let us know that the answer was clear and we can proceed. So, all right, so up next, we have Francesco Riva. Can you test the mic? Yep. Okay, we can hear you.
Can you hear me? Good.
Yep. It's good. Good. Yeah. Looks good.
You can see my screen.
Yep.
Good.
Okay, so Francesco is going to tell us about the IR side of positivity bounds. Please take it away, Francesco.
Thank you very much for the invitation, to all of you for being here. You can see my pointer. Is that okay? No.
Yes.
Yes. Good. Thanks. Okay, so I will hopefully complement a little bit what we've heard so far with a more dedicated discussion to loop effects in the infrared. So the way that we sometimes think about effective field theories is in theories which are characterized by a weak coupling, and we know the UV, for instance, in the electroweak theory, and in which we can match this electroweak theory below the mass of the W and Z bosons into an effective field theory, Fermi theory, which is both simple and predictive. It is predictive in part because its coefficient can be written in terms of the known parameters in the UV. And it's simple just because it's an effective field theory. So you have a small parameter around which to expand the energy expansion. However, in many cases that we're interested in, like in physics beyond the standard model, in which we would like to capture features from unknown physics at microscopic scales, or in quantum gravity, which is similar, or in chiral perturbation theory, we deal with situations in which the UV is either not known or it's not calculable. And in this case, the matching to the infrared is lost. So we're still left with something which is associated with a small parameter, but is not so predictive because it's characterized by an infinite number of Wilson coefficients that we cannot really control. And so dispersion relations are a tool that allows us to assume a minimal set of fundamental hypotheses in the UV and allows us to identify a set of effective field theory which are somehow testable, so to reduce the parameter space of these effective field theories. So I will not talk about gravity, unfortunately, and I will instead work around this simple example in which we scatter a simple spin zero particle of single flavor, in which the amplitude at tree level can be written in this form. Fortunately, I use the same notation as David. The first coupling is the coupling strength of a single U1 Goldstone boson, as you might recognize. And the second one instead is the coupling that would characterize a particle which manifests this Galilean symmetry. It's something that you find in massive or modified gravity. So it's phenomenologically quite interesting to understand what the values of this coupling can be from fundamental principles in the UV. So let me quickly review the bounds that we can draw for these few parameters. We have bounds from the forward limit, as we have heard in the previous talk, that are just positivity of these coefficients. And also the fact that these coefficients, when you go higher and higher in the number of powers of energies, they decrease monotonically in units of the cutoff. This was mentioned before as the fact that dimensional analysis is a theorem. We can also, there are also bounds that exploit information beyond the forward limit, and this implies that this coefficient cannot be arbitrarily positive in terms of G2 and the cutoff. And also, exploiting crossing symmetry between all the possible channel. It's been shown in this various paper that it cannot be arbitrarily large either. Okay, so when we put all these bounds on just these three coefficients together, they nicely appear in this two-dimensional plane where we have G4 is the coefficient here, G3 is this one here, and G2 just sets the units, and they give us this sharp island of positivity bounds. Okay, so the question that I will address in this talk is whether calculable infrared loops modify this island, and in particular I will focus on the leading contribution of this loop, the loop of the most relevant interaction in this theory. This is the most relevant interaction in the theory of a Goldstone boson, but of course you can have like a lambda 5 to the 4 interaction perturbing this. We can discuss about this later. It's not such an interesting thing. It doesn't modify very much what I'm going to tell you. So I'll focus for the moment on this one. If we include these effects, the amplitude gets modified by these some logs. And in particular, what I'm gonna look in this talk is how the bounds are going to be modified. And as a spoiler, the bounds on the G2 positivity, this is not affected. The one on G4 is affected only mildly if you consider the running coupling instead of the physical coupling. And my question is mostly focused on how the bound on this G3 coupling gets modified by loop effects. Okay. So I will start repeating a little bit this thing of dispersion relation just to set the notation. So I will go faster through the slides. But the idea is the one in which we take assumptions of causality and unitarity in the, well, of the whole amplitude at all energies, and we translate it into some properties of the amplitude in the complex S plane. And in particular, the non-analyticities of the amplitude in this plane are characterized by a UV part, which was discussed also in the previous talk, because of the exchange of some heavy particles and so on, but also an infrared part, which is calculable and associated with loops in the effective field theory. Because of crossing, the same type of non-analyticity is found also on the negative real axis. And in particular, there's also a pole here because we're going to do subtractions of the amplitude in this crossing symmetric point. So this complex S plane is divided into two areas, one which we can call UV, the blue one, and one, the red one, which is infrared. In the infrared one, we can compute things with the effective field theory. Instead, in the blue one, we cannot, and we just have to rely on properties of the amplitude to understand what goes on. We, considering this contour and assuming these boundness properties in the UV for which this contour at infinity vanishes, we can then relate this arc integral with integrals over the positivity, the real axis. So in practice, this is the whole talk is about this. Considering quantities which are calculable in the effective field theory, integrals along this arc, and are equal to a UV representation that is not calculable. So more explicitly, this is written here, the infrared part and the UV part. And these, I will refer to them sometimes as arcs, just because they look like arcs in the IR representation. So the name of the game here would be to try to identify positive quantities here on the right-hand side. For instance, at t equals 0, we know that the imaginary part is positive. So arcs are positive at t equals 0, and this can be translated into a property also of the infrared that we can think as a consistency condition for the effective field theory. Okay, so any positive relation in the UV will give us a consistency condition in the effective field theory. And it's all about finding all possible positive relations in the UV. So now that you see where the bounds come from, let me discuss a little bit more the IR. So compute these arcs in their IR representation. This is just an integral in the complex plane given by this function. If you know the amplitude, this is it's straightforward. And interestingly, these things are measurable in the effective field theory. And also they are directly related to the UV, as we saw before. So if I were an experimentalist, I will actually use this type of quantities I will try to measure this thing and reconstruct these things, and to have a more predictive quantities on which to base my experiments. But as theorists, we are also interested in the fact that arcs are in some way related to the Lagrangians, so that we can compare with microscopic theories and so on. And in particular, at 3 level, the only singularities in this infrared region come from the subtractions at this point here, this crossing symmetric point. So there is a one-to-one correspondence between these arcs and the coefficients, the Wilson coefficients in the IR Lagrangian. Indeed, the amplitude is what I wrote already in the first slide, and then around t equals 0, the arcs are in one-to-one correspondence with these coefficients. So you see the 0th arc is just G2, and for every Wilson coefficient is picked up by one of the arcs. So we have this situation in which sharp bounds on the arcs that I will discuss later translate into sharp bounds on the Wilson coefficients. Now, this is very interesting, I think, because these arcs, this approach gives you the feeling that you can individually pick every single coefficient in your effective field theory expansion without any assumption, without assuming that this series converges or whatever. Each coefficient is related to one arc, and one arc will have its own bound. So the situation is very clean. When we actually go and include loop effects, the analytic structure in the IR changes. It includes now these branch cuts here. And in particular, the situation is different because we have in the amplitude, so this branch cut correspond to these logarithms here. And this beautiful clean picture in which to each arc we had one coefficient is now completely is now lost, because every single coefficient enters in every single arc. So we no longer have a finite expression, but we have expression involving infinitely many terms. So this means that somehow, if we still want to express bounds on the Wilson coefficient, and when we include loop effects, we have to make certain assumptions about convergence. These assumptions are similar to those that we make when we say that the amplitude in the effective field theory is truncated at the first few orders. These are assumptions of convergence, but still we lose this very nice relationship between in which we can single out every single Wilson coefficient. There is another feature that comes out at loop level, which is that some of these arcs and their derivatives around t equals 0, they happen to be singular. For instance, in the second derivative of the 0th arc, there are terms like this one, like this log of 1/t, that is singular around t equals 0. And these infrared singularities are picked by the arcs. So in this talk, I will focus mostly about this aspect and understand how these infrared singularities, they propagate along the bounds. As I understand, Ricardo will talk more about this idea of assumptions that have to be made in his talk on Wednesday. Okay, so the question is, which bounds are affected by these singularities? And I will discuss these UV bounds in 2 different ways. In a first approach, I will be slightly more conservative than what was mentioned in the previous talk, and I will only look at the region around t equals 0, where it's been proven that the amplitude is analytic in S. And later I will also discuss instead when we can extend the analyticity region, as mentioned before. So there are many works that take this approach of looking at the amplitude and objects similar to the arcs.
Sorry, I have a question.
Yes.
Generally, if you do the partial wave expansion, you don't need to, look at the forward limit. Is that right?
Yeah, I will not just talk about the forward limit. I will actually introduce the partial wave expansion in a moment. So yes, you're right. It will appear in the next slide. So it's not going to be
Yeah.
about the forward loop.
My point is that if the t don't go to 0, so you don't need to care about the divergence. We'll do the partial wave expansion.
Very good. Yes, I hope it will be clear in a couple of slides how this behaves. I will take two different approaches for the bounds. One in which it will be t close to 0, and then I will tell you what the differences are t different from 0. So if you give me just a couple of minutes, I hope it will
Francesco, you only have 8 minutes, including questions left, so we can take the questions at the end. Okay, good. Yeah. Okay, so there are many approaches that expand around t equals 0. I will give you here one look into it. So we have an infrared expression for the amplitude, and we have a UV expression for the amplitude that we can expand in partial waves. The imaginary part of partial wave is positive, and these are known objects that we themselves can be expanded in powers of t in terms of known coefficients. The beautiful thing about this expansion is that the objects that we have here appearing in this series, these are integrals over S and over L of powers of L of S. And these are called moments. You all know what a moment is, but let me remind you of its beautiful properties. Moments are integrals over positive distribution of powers of X. Think, for instance, of a mass distribution, like an asteroid or a rock. So the 0 moment is the total mass, m, and sets the units. The first moment is the center of mass, and is maximized when all the mass is here. And the second moment is the moment of inertia, and is maximized when all the mass is distributed on a ring, as it's always smaller than r squared m. So these three moments, they cannot take arbitrary values because their bounds are given by two quantities, m and r, and they must lie in this region above this parabola. If r is known and is compact, is limited, then we also have an upper bound here. Okay. Now, okay, so the moments that we have here on the right-hand side of our dispersion relation, they are 2D moments, one variable which is compact and the other one which is not. Okay, so when we look at this now, at the dispersion relation, in the infrared, we can write it as a simple expression in terms of these infrared parameters. And in the UV, it can be written in terms of these moments. In whitish are things that just complicate the discussion and are not relevant for now. And in blue, you see 0, 0, mu 1, 1, mu 2, 2, and these lie on a parabola, exactly as I showed you here. There is lower bound, but there's no upper bound. Francesco, you have 5 minutes left. Just
yeah, the first arc is also given in terms of the same parameters. So these people have shown that by using full crossing symmetry, you can exploit the equivalence in the infrared, also in the UV. And because this guy is smaller than this one, we now have an upper bound here, and this translates into an upper bound on mu 1, 1, which is the coefficient linearly in T, and so also a bound on G3. Sorry. Okay, as you'll see down here, okay? Good. When we go at loop level, we introduced functions which are non-analytic in T, and I regulate here by a small mass parameter that is just here so that this slide makes sense, and appears in the arc here, and disrupts this crossing symmetric relation between these two pieces and also the UV pieces. So when we actually plot the bounds as a function of the mass, when the mass goes to 0, the bound disappears. Okay. There is a different way of seeing this bounds in the UV, which is, as was done in the previous talk, to assume that the amplitude is analytic in S also for finite large T. And I will show you a slightly different approach, but that complements this finite impact parameter bounds that were explained before, and is the following. The infrared parameterization remains the same, and in the UV now we work at finite T, negative T. This thing is not positive, so in principle you don't see positivity bounds there, but it's bounded, And in fact, when you plot these Legendre polynomials for all else for negative t, you see that they cannot take any value. They're always smaller than 1, and they're always bigger than -1/2. So the integrand that you see here on the right-hand side has to lie within this trumpet here, okay? Normalized in units of this arc at t = 0. In the infrared, we can compute the arc, as I gave you in the previous slide, and is given by this expression plus more and more terms. So if we limit at the linear order, it's just this line. When we compare UV and IR, this red line must stay within the trumpet. So we get a lower bound corresponding to an upper bound on the line, which is this -3/2. And from the lower part, we get an upper bound, which is something of order 5. Now, the interesting thing is that these bounds, in particular the upper one, comes from the region of finite t. So when we now include loop effects, and in particular these singular logs, the loop effects are finite at finite t. And therefore we get something which is not singular at t = 0 and the bound is still there. Moreover, the bound, the lower bound is dominated from the region of t = 0, but relies only on the first derivative of the arc, which is finite. So you get this beautiful picture in which the quantity that we're looking at, which is this G3, is bounded from above and from below, also for finite loop effects. This is the size of the loop, roughly. When we're here to 1, this is non-perturbative, it's not so interesting. But for any finite value, we have a finite bound on this thing.
Francesco,
I guess
could you wrap up? We have time for some questions.
Yeah, good. Let me run to the conclusion. This is some other stuff that perhaps we can discuss later. So the conclusion is just the fact that when arcs have sharp bounds, Wilson coefficients do not. They change in the presence of loops. But when we look in particular bounds of this G3 over G2, if we assume that the amplitude is analytic only around t = 0, then the bound disappears as m is sent to 0. Instead, if we are able to assume that it's analytic also for large negative t, the bound remains, and this idea of Galileans, they must have a small cutoff and a small region of validity. Okay, that's roughly it. So, yeah. Thank you.
Any questions? Again, just as a reminder, there's a Slack channel. Maybe we can post a link on the chat for everyone. So there's further discussion there, and if anyone wants to ask questions. We have time for maybe one quick question.
I think someone on Zoom.
Oh, yes. Go ahead.
Me?
Yeah.
Yeah. Okay, great. So I have a question. Maybe it's a bit naive. Is that if you integrate from a IR cut instead of a UV cut, can you cancel this log terms? Because I think if you integrate from IR cut, we can reproduce the one loop calculation, so it might cancel the logarithmic terms.
No, basically, if you're integrating from the infrared, I mean, then you're evaluating the amplitude at s = 0, right? So your little arc would have a radius 0. There are several things that happen. First of all, here the energy scale that appears here is going to be 0, so the bound disappears, right? And then you're really only sensible to the coefficient in the pure IR, so you will still have this type of effects. There are some logs that disappear, you're right, that correspond to the integration over the branch cut from 0 to the cutoff, but these are different. These are collinear logs in which t is very small compared to s, so it doesn't really depend on the radius of your integration, but it depends on the value of t. So yeah.
I see. Great. Thanks.
Thank you.
Okay, let's thank Francesco again.
Thank you.